Okay, so let's start talking about precipitation reactions. We've talked about the way things are soluble in water and started with this idea of solubility and how we can have solutions. You may also remember that we can have suspensions and mixtures, things like that. Precipitation reactions, we're going to revisit. We looked at them briefly in Year 10 science, but now we're going to start making sure we can write reactions that show the formation of the precipitate. And the solubility table rules that we were given in Year 10 aren't actually given to us in Year 11. We need to memorize them. So let's start having a look. So we've talked about the fact that when we were talking about bonding, that a number of ionic solids are soluble in water. And we said that when we talked about solubility, that ionic compounds dissociate, which is that ions that were trapped in the lattice are then freed up to become aqueous ions, and we write a dissociation equation like this. Okay, remembering that when ions are dissolved in water, that the negative end of the dipole of the water molecule will interact with the positive ion and surround that ion in a hydration sphere or hydration shell, and that the interactions between the ion and the dipoles of the polar water molecules are ion-dipole interactions. So this is what occurs when we have a soluble compound. The ion-dipole interactions between the ion and the dipole of the water is sufficient that it can overcome some of the hydrogen bonds in the water molecule between the water molecules, such that the ions are dissolved into solution, and we will not be able to identify the particulates, that this will be clear, it may be colored, but we won't be able to see individual particles, and that the ions will be floating in a solvent of water where the bulk of the solution is actually water. Okay, so this is when they're soluble. There are different ionic compounds that are insoluble in water. Okay, and if you think about this, you know of some, marble being one that we use for carving statues, and seashells are also insoluble. Limestone caves, these kinds of things form from precipitation reactions. And in Year 10, we learnt about double displacement reactions and how a large number of these actually form precipitates, where we have compound A, which will be a solution, so it'll be an aqueous solution of an ionic compound, and compound B, which would be a aqueous solution. And when we put them together, we will get compound C and D, one of which would be aqueous and one will be solid. And the one that forms a solid we refer to as the precipitate. Okay, remembering that they swap partners, so the cation of one reacts with the anion of the other, and the anion of that one will form with the cation of this one, forming two new ionic compounds. Okay, one of which is soluble, which would be C here, and one is insoluble. Okay, remembering that C will now be a dissociated ionic compound, so it would be like our NaCl example up here, where we would have aqueous solutions of sodium ions and aqueous solutions of chloride ions, whereas our D would be a solid that would form in the bottom of the test tube or the container. Okay, so the solubility rules that we looked at briefly in Year 10 are how we can determine if the products of such a reaction will be soluble or insoluble. So there are a series of rules that tell us whether or not the new compounds would be soluble. So as I mentioned, these solubility rules are not ones that you are going to be given in year 11. They're not in your data booklet, so you actually have to remember them. You need to memorize them. So one of the ways that we can remember it is using good old Professor Snape, okay? And this is a mnemonic that helps us to remember them. That is that compounds containing sodium, nitrate, ammonium, potassium, or ethanoate are going to be soluble compounds, okay? So that means they will not form precipitates. So anything that has a sodium cation, so NaCl, NaBr, all of these, it doesn't matter what the anion is, these will always be soluble. Okay, which is good because if we remember the ones that are always soluble, there's no exceptions to those. Okay, all nitrates are soluble, all group 1 compounds are soluble, so this includes our sodium, but also potassium. Okay, so these ones are our group 1s here. Okay, and ammonium compounds are soluble. If we remember this, these ones, there are no exceptions to this. They are always soluble if it contains an NH4 plus ion, a Na plus K plus, or an NO3 minus ion. The ionic compound that has the alternative to that will always be soluble. Okay, the thing that's important to remember, solubility is a scale, so when things are said to be insoluble, they may have partial solubility. Okay, so they may only be soluble in warm water or hot water, things like that. So it is a range. When you're predicting, you're just using generalizations. So if these ones are always soluble, the ones that are insoluble, we can remember by the term CHOPS. So this will be carbonates, hydroxides, oxides, phosphates, and sulfates. There are some exceptions to the insoluble ones though. So the Snape, always soluble. CHOPS, we've got some exceptions. These are all listed in your textbook on page 323, and I strongly encourage you to make a flashcard or Quizlet or something like this to help you remember them. So if we have a look here, we can see all nitrates, ammonium, sodium and potassium, and ethanoates, that's our E for our Snape. Okay, ethanoate, CH3COO minus. These are always soluble. Most sulfates, and this is where I always get this one wrong, because the S in CHOPS is not sulfates, it's sulfides. Don't make the same mistake I do. Okay, because most sulfates are soluble, but there are some exceptions, which is why they don't go in our always. Okay, so most sulfates, and I like to remember this by the fact that we're all familiar with copper sulfate, blue solution, so we know it's soluble. Okay, and the ones that are insoluble are our heavy metals. Okay, so things that are large and heavy, so lead, barium, strontium, and then also silver is a common one in these. These are common exceptions to solubility. You'll see again up here that most halides are soluble, but silver is always our exception, and lead. Okay, so lead chlorides, lead bromides, lead iodides are all insoluble. Silver bromides and silver chlorides are insoluble. So the general insoluble ones, most hydroxides, okay, so remember this is Snape for this table and CHOPS for this table. Okay, so hydroxides is our H, and that's sodium hydroxides, potassium hydroxides. These ones are all soluble because they come from our Snape rule. Okay, but in general, the other ones are insoluble, with calcium and strontium being exceptions there. Carbonates are mostly insoluble. There are no exceptions other than our Snapes. Okay, phosphates, again, it is just our snapes that are the exception. Sulfides, just our snapes that are the exception. So carbonates, hydroxides, then there's oxides, which aren't on this table, phosphate, and sulfides. These are your insolubles. Okay, so H, this is your C, P, and S. Okay, and then oxides for chops. Okay, the exceptions here are Snape. These ones, they're always Snape. And there's just these ones which are slightly soluble that are a little bit odd. But if you can remember Snape and chops, you are going to be able to answer the majority of questions that ask you which one would be the precipitate. Okay, so make sure you pay attention to this. So let's have a quick look at precipitation reactions. You should remember a lot of this from year 10, but let's review them anyway. So a precipitate is a solid that may form when two solutions react. So this is two aqueous solutions. So the full balanced equation is barium chloride plus sodium sulfate is going to react to form barium sulfate and sodium chloride. Sodium is a Snape, so we know it will be aqueous. Sulfates are mostly soluble, but barium is always one of our exceptions. It's a heavy metal, so this one is going to be our precipitate. So barium sulfate is going to be insoluble and will form a white precipitate like this one here. This is classic of barium sulfate. Sodium chloride is going to be soluble, so it will be in solution as sodium, aqueous sodium ions and aqueous chloride ions. Okay, because these ions remain aqueous on both sides, so here we would have Ba2 plus, 2Cl minus, and then 2 Na plus and SO4 2 minus. All of these are aqueous on the left hand side. When we get to the right hand side, however, we get BaSO4 solid. So the sulfate and the barium have gone from aqueous to solid. The sodium chloride, however, these are still Na plus, Cl minus. Because they are aqueous on both sides, we can actually remove them. They are referred to as spectator ions. They have done nothing in the reaction. They started out as Na plus ions in solution and ended up as Na plus ions in solution, started out as chloride ions in solution and ended up as chloride ions in solution. So this means that they didn't participate, so we refer to them as spectator ions. Okay, so have a go, pause the video, have a go at doing these checkpoint questions from your textbook on page 31 on predicting the precipitate. For now, use your solubility table, but remember you do need to try and start remembering these as much as possible.